Hi everyone, welcome back for another video. Let us do question 6 from the January 2020 CSEC Physics paper 2. So for part A is telling us that there are 3 emissions, alpha, beta, and gamma, from a radioactive source, and they're subjected to a uniform magnetic field that's perpendicular to their path, right? And that's shown in this figure here, figure 5, right? So here we have, let's look at figure 5 right away. We have our radioactive source down here. It's in a uniform magnetic field that's perpendicular to the path that these emissions are gonna take, right? So draw the 3 rays to represent the path of each of the 3 emissions, alpha, beta, gamma, and then just show them on the figure 5 as they pass through the magnetic field, right? So we're focused on a magnetic field here now, right? And so with magnetic fields, we know that there's gonna be a force, right, that the particle feels based on its charge, right, once it's placed in that magnetic field, and that force will then determine the path that the emission takes, right? And so in the case of the gamma, what do we know about gamma? We know that gamma doesn't have a specific charge, it's neutral, it has a mass, but it's not gonna be deflected in that magnetic field solely by virtue of the fact that it's uncharged, and so it won't feel a force per se from this magnetic field, and so it will just go straight through the field undeflected, right? So this is our gamma. Remember now, gamma doesn't have any charge, and so once it interacts with that magnetic field, it won't feel any force, and so it won't get deflected anyway, right? So now let's look at our alpha particle, as shown here by this magenta. So our alpha particle, once it encounters that magnetic field, it's only slightly deflected, but it is deflected, right? And that's because alpha particles are positively charged, right? And so when they encounter a magnetic field, they will interact with the field and they will feel a force, right? And so they're deflected, but not as greatly as in the case of a beta particle. And the reason for that is that beta particles, of course, we know they have charge, they're negatively charged, but they're also very, very light, right, compared to alpha. So alpha particles, what we liken to a helium nucleus of mass 4, and a beta particle we liken to an electron that doesn't really have any mass, right? And so once we encounter this magnetic field, we couple the fact that the beta particle has a charge and is very light, it's going to experience a great degree of deflection, a greater degree of deflection than the alpha. And of course, it will be going in an opposite direction because they have different charges, okay? So this is how we would show the interaction of these emissions in a uniform magnetic field, right? So that's what we drew here. Remember, the key thing here is that the gamma is undeflected, the alpha is slightly deflected, and then the beta is largely deflected, okay? And that has to do with their charges and their masses, okay? Okay, so moving down to part 2 now, the magnetic field that we previously had up here was then replaced by an electric field, and that electric field is shown in figure 6. So let's look at our electric field now. So again, this is figure 6. We have our radioactive source here. So this is where our alpha, beta, and gamma particles will be coming from. And then we have an electric field. So we see that we have a positive plate here, and we have a negative terminal here. And so, of course, you know, the field lines for an electric field are going to go from our positive to our negative. And so this black line represents those field lines, right? Those electric field lines. And so the question is asking us then to draw the 3 rays to represent the path of each of the 3 emissions, alpha, beta, gamma, on figure 6 as they pass through the electric field, okay? So again, our particles are coming from down here, And again, the gamma is going to be undeviated, undeflected, undisturbed by that electric field once it passes through. And that's because it doesn't have any charge, right? So if it's an uncharged particle going through an electric field, then there's no interaction there to be had. And so it will just continue on its path straight up like this, okay? Now, let's look at an alpha, right? If we have an alpha particle, remember we said alpha particles are positively charged. They're likened to a helium nucleus that has a plus, what is that? A +2 charge, right? So this will have a +2 charge on it. And then the beta we liken to an electron that has just a negative charge, right? So the alpha has a +2 charge on it because we liken that to a helium nucleus. And so it's going to want to go towards the negative portion, the negative plate. So we see that alpha goes over here because it's positive, it's going towards the negative plate. And so as a result of that, we see the deflection in this direction. And again, by virtue of its mass, remember it has a mass number of 4, right? So it's fairly heavy when compared to the beta particle, so it won't be deflected as much, right, as the beta will be, right? But the beta now, remember we said the beta now is like an electron, so it has a negative charge. It's going to want to go towards the positive plate, so that's why we draw our arrow for beta coming towards the positive plate. It's going to be deviated significantly, right, because it has no mass, right? It's virtually 0 for its mass, right? So mass of virtually 0, charge of virtually minus, of essentially -1 because it's like an electron, so it will go towards the positive plate. We'll see a lot of deflection because the mass, it's so tiny, right, that it will just get deflected to a great extent once it encounters the electric field. And again, over here, we said that the alpha is likened to a helium nucleus that has a charge of +2, so it's positively charged, will move towards a negative plate, and has a mass of around 4, so that's fairly heavy. So it's not going to be deflected as much as you would see for the beta, which has virtually no mass, okay? So that's all that we needed to draw here for part 2. And we would have gotten our 3 marks there, okay? So let's move on down to see what the rest of the question is about. So let's move on to part B now. So part B is saying that there's an unstable isotope of lead. So that's lead 21082 Pb, right? So that's 21082. This is the mass number. This is the atomic number. And we have this unstable isotope of lead that undergoes exactly 2 sequential beta particle decays. And then that's followed up by an alpha decay, alpha particle decay, to then become stable lead 20682. Okay? So, with reference to the information in table 3, write the nuclear equations that will result in the formation of stable lead, right? So this is the stable lead from this unstable one, right? So remember when we talk about radioactivity and radioactive isotope, we said there's an unstable nuclei, right, that wants to become stable. And so to do that, it goes through these emissions of what we call radioactive emissions to end up with a stable form. And so that's exactly what's happening here. We're taking this unstable one, it's gonna emit a beta and then another beta after that, and then an alpha to ultimately give us the stable form. Okay, so that's what's happening here in a nutshell. So we look at this table 3, right? Table 3 is telling us that whenever there's an atomic number, right, of 83, then that element would be bismuth. And then if there's an atomic number of 84 that results from that decay, then we will have the element polonium. Okay, so we just have to keep these things in our minds as we write these decay equations, right? So, okay, so for the first beta decay equation, remember now we're starting with 21082 lead. So we write that as our starting point, right? Or our parent nuclide. This is the one that we're starting with. We're going to undergo a beta decay. And whenever we undergo a beta decay, our atomic number is going to increase by 1, right? So we reflect that here, that our atomic number is going to go from 82 to 83. our mass number is going to be unchanged, right? And so if we refer to this table, we'll see that whenever we have an atomic number of 83, that's bismuth, right? That's a completely different element that we're forming. So we get bismuth, which is 21083, and of course our beta particle that was emitted to form it, okay? So similarly, we have a second beta decay. We're starting with our bismuth, in this case, 21083 bismuth. And we're gonna go now, another beta decay. So we're gonna go by 1 again in our atomic number. And so we end up having 21084. And whenever we have an atomic number of 84, that's polonium now. So we write polonium as our element beside that, okay? So we have 21084 polonium, and of course our beta particle that was emitted to form that polonium, okay? So then finally, we're gonna take this polonium now, and then it's gonna undergo an alpha decay now. And remember, whenever we undergo alpha decay, our mass number decreases by 4, and our atomic number decreases by 2, and that's because we are literally giving off this helium nuclide or this alpha particle, which has this particular mass, okay? So we go from 210 to 206, we go from 84 to 82, and this is our stable lead, right? That's what the question told us, that the stable lead is the one that has the mass number 206 and the atomic number 82. And so this is all that we need to show for 6 marks, okay? So we're good with our 6 marks here. And so moving along to part C is asking us to calculate the energy given off in a nuclear reaction if the change in mass is 0.3018 U. Okay? So remember, whenever we said that the change in mass, right, is really what causes energy to be generated by these nuclear reactions. And so if we are being asked to calculate an energy, we have to then use Einstein's equation, because that's the equation that relates this energy to the change in mass, right? So that's just delta E is equal to delta MC squared. Okay, so the question itself, in it, they gave us what the change in mass is. They told us that it's 0.3018 U. And so you might realize that this is not an SI unit. And we know that energy is in joules, is an SI unit that they want this answer. And so they gave us the equivalent of what 1 U would be in kilograms, and that's 1.66 times 10 to the negative 27 kilograms. And so in order to go from 0.3018 to kilograms, what we have to do is simply just multiply this by 1.66 times 10 to the negative 27 kilograms. And so we end up getting our change in mass in kilograms. So that's our first step, is to convert this atomic mass units of U to kilograms. And so we did that here. And so we ended up with a delta M of 5.00988 times 10 to the negative 28 kilograms. So now we're in SI units, right? Okay, so all that we have to do from here is come over here now and plug in this delta M in our Einstein equation. And so delta E then ends up being equal to 5.00988 times 10 to the negative 28, right? And then we're going to multiply that now by the square of the speed of light, right? So we square the speed of light and multiply that by our delta M, and we'll come out with what our delta E is, or the energy given off in this nuclear reaction, as 4.50 times 10 to the negative 11 joules. So that's our answer, guys, right? For these types of questions, just realizing, okay, if I have a change in mass, or what we call a mass defect, then I'll have a change in energy, or energy will be given off as well. And we can relate that mass defect to the energy change by Einstein's equation here. And then from there on, it's pretty much just a matter of plugging in numbers, right? But the key thing that you have to do is just remember that if they give you the mass in just atomic mass units or U, you'll have to convert that to kilogram first. And they give you that equivalence of 1.66 times 10 to the negative 27 kilograms. So just keep those things in mind whenever you're encountered with a question of this nature, and you'll always be fine, okay? So that was worth 3 marks, a total of 15 marks, and we are done with this question. So as usual, drop a comment down below. Let me know if this was clear to you or if there's anything that's unclear. And of course, give this video a like, subscribe to the channel, and I will see you in the next video.